Welcome everyone to today's webinar on what's new in Q-Chem 7 by Professor Martin Hedgorden. Okay, so just a quick reminder that during the webinar, attendees can post their questions in the Q&A section, and this will be answered at the end of the webinar. And if you have any questions during the about today's topic, please contact us. So either at my email or support@qchem.com, or you can post your questions at the Q-Chem Talk forum. And so today's webinar will be recorded, and the video will be uploaded on Q-Chem's website and our YouTube channel in a few days. So now let me introduce the speaker. So today's webinar is given by Professor Martin Hedgorden, who is the Kenneth S. Pitzer's Distinguished Professor of Chemistry at the University of Berkeley. He's the scientific advisor at Q-Chem. His research group centers on the development of new electronic structure theory methods and their implementation as efficient computer codes. And is recognized with many awards, including the Medal of the International Academy of Quantum Molecular Sciences in 1998 and the Warthog's Schrödinger Medal in 2020. So he has been involved in Q-Chem for over 30 years and is one of the founders of Q-Chem. So with that, I'll hand it over to Professor Hedgorden.
Okay, well, thank you, Kaushik. And let me share my screen here and let's take it away. So hopefully you can all see a beautiful slide, and I must start by acknowledging Dr. Shannon Hauk at Q-Chem for a lot of help with slide preparation. These slides are as much hers as they are mine, so thank you, Shannon, and I'll have other acknowledgements as we go along. So what are we going to be covering today? Well, essentially all about Q-Chem 7, which is our major release. It's been out for less than a month, and we're super excited about it. So my main job today is to try and share a bit of our collective excitement with you guys and let you know something about, I can't tell you everything about Q-Chem 7 because it's like, covering what's inside 8 million lines of code is completely impossible in the amount of time we've got, but we'll go through some highlights inside Q-Chem 7. That'll be the majority of the talk. And then at the end, I have very special highlights, which is Q-Chem 7 comes with two external packages, brand new packages, QC-PBC and MChem, that I want to tell you about. And so that's basically our agenda, and then we'll go to questions. All right, so presumably most of you know all about Q-Chem, but I'm still required to tell you a little bit about it. So back in 1992, there was kind of a messy software divorce that involved the Gaussian program, which I used to work on, and three of us struck out in a new direction, and we have managed to sustain this direction that has become the Q-Chem code over now a period of nearly 35 years. And Anna Krylov is Q-Chem's president, and there's a board of directors that represent academic developers and also financial expertise in the form of Hilary Popel. And there's an extensive academic network symbolized by by all these little blue markers on the world map. And Q-Chem's an open teamware project. In other words, if you are interested in developing in Q-Chem and don't currently now, the door is open to you. We don't have any barriers. All you need is a valid license and a very simple non-disclosure agreement. Our academic team is supported crucially by a commercial team, the team of professional scientists and office staff who run the Q-Chem office. And so how does Q-Chem go about distributing the results of our development? Well, we typically do a major release once a year, and that is around the end of, somewhere between May and June. And then we'll do two minor releases to kind of small additional features, bug fixes, updates later in the year. And then about every 5 years, we have a generational release. And so 2026 is a generational release year for us. And so that's really why we're all here, Q-Chem 7. And here's my acknowledgement slide. The actual development, here I am, one person trying to tell you about this giant collective effort. And really the point is it takes a village. And the village is organized through the Q-Chem office and through this development network. And you'll hear about various particular contributors. But if I don't mention someone who's listening who is a contributor, let me apologize due to lack of time, but everybody is important in a collective effort like this. Q-Chem distributes its software directly. You can run it, for instance, through a shell in Linux or Unix. You can also use a graphical front end. Our own is IQmol, which is available at iqmol.org. You can access Q-Chem through the cloud. And then we have a very special partnership with Wavefunction, a developer of advanced graphical user interfaces and molecular modeling software. You can visit their website at wavefun.com, and Q-Chem is the electronic structure engine behind their Spartan 26 modeling package, and as well as all of the ones that predated that. If you are wanting to use Q-Chem and you have no money to buy either a machine or software for it, you can access Q-Chem at no cost on supercomputing facilities, and you can use Q-Chem's own servers through the IQmol front end for small scale pilot calculations. So we've got various access models, and then we hope that many of you listening will buy Q-Chem 7 licenses, and then if you want to upgrade those to become developer licenses, that's possible at no additional cost. Visit our website, qchem.com, for all the details, but in brief, our 30-odd years of history have made us into a leading electronic structure code that specializes in DFT, but also beyond into many-body theory, coupled cluster theory, excited states, all of the tools that you need to walk on potential energy surfaces and to model complex environments, and a bunch of unique tools that include the nuclear electronic orbital models that come out of Sharon Hammer-Schiffer's group, a whole bunch of spectroscopy, both valence electron and core electron spectroscopy, and most of all, efficient algorithms. But yeah, that's kind of the general backdrop. And with that out of the way, let's begin to jump into some of the highlights in Q-Chem 7. And probably density functional theory is the core of modern quantum chemistry, and so I'll spend most of my time focused on density functional theory features because they're most important to most people. But this is by no means all of our features, and so I will say a bit about other things. The main reason why you should use Q-Chem in your research is because it is the best we have the best infrastructure for density functional theory calculations, the biggest range of functionals, the best algorithms, and more than that, these are algorithms you can depend on. So I want to highlight Kaushik, who introduced me here, Kaushik's work on infrastructure here, and remind you probably what you already know, which is the defaults of quantum chemistry codes are typically optimized for speed rather than robustness. And this affects reliability. It affects the success rate in large-scale workflows and in big data projects. Another issue is that orbital stability analysis is key for density functional theory accuracy. For instance, if you don't let the orbitals spin polarized, your barriers have demonstrably bigger errors than if you do let them spin polarized. In other words, you don't get the best chemistry you can get. And Kaushik has led efforts at Q-Chem to provide a meaningful solution to these problems, which is the part of Q-Chem's infrastructure that I want to highlight here, which is by setting SCF underscore algorithm to be robust or robust underscore stable, you can have Q-Chem's defaults and algorithms auto-tune. That is, they run as fast as they can under normal conditions. And then if trouble is encountered in the form of oscillating SCFs or divergence, then tolerances are tightened, algorithms may be changed, and the number of SCF cycles that are allowed will auto-adjust. And this is a super important tool. And it underscores the fact that you can get your DFT calculations to converge. Now, what kind of DFT calculations? Well, Q-Chem's got literally hundreds of functionals, but one that is worth highlighting is this coach functional. This coach is an acronym for carefully optimized and appropriately constrained, and it's a hybrid, so that makes coach. And we believe it is the most accurate hybrid functional yet. It is of the range-separated hybrid class, so this is outgrowth of my group's work on range-separated hybrids. So I'm highlighting here omega B97M-V as a very good existing hybrid. You're staring at what we call normalized error ratios, which is the average of the second to the fourth best across 137 data sets. And so to beat the average of the second to the fourth best functional on any given data set would imply a normalized error ratio less than 1, which is really, really good. So for instance, you could look at B3-LIP, a common density functional, and its mean normalized error ratio is about 2. So in other words, in an RMS sense, 2 times worse on average than the second to the fourth best of our 16 tested hybrids. And in some cases, it's better, like frequencies. You know, B3-LIP frequencies are good, and the statistics say they are. In other cases, they're worse. Barrier heights, B3-LIP barrier heights are not very good. Then you come to a state-of-the-art hybrid, omega B97M-V, that you still can't run in some of our rival codes. Yet another good reason for not using those rival codes. If they can't run the best functionals, why should you run those codes? And at the moment, I believe no other code apart from Q-Chem 7 can run the coach functional, which, as you can see, improves by about 15% over omega B97M-V. And so arguably is the most accurate hybrid functional yet. The improvements are particularly noticeable for transition metal chemistry, also for barrier heights, very useful, and electric field properties, which was a class of property not represented in the data used to train and then validate omega B97M-V. By the way, coach obeys 11 exact conditions, and omega B97M-V only obeys 5. We also include the latest and greatest Minnesota functional, CF22D, which is a significant improvement over any other Minnesota functional. And so this just helps you do good chemistry in conjunction with all the other infrastructure, which I now need to walk you through. If you are interested in doing highly accurate DFT calculations on big molecules, you know it's expensive. You know you need big basis sets in order to approach the complete basis set limit at which the functionals are trained. I'm super excited to tell you that Q-Chem now has we believe the world's at least equal best semi-numerical exact exchange code. And this is work done in my group by Jesse DiCenzo and Henrik Lacroix. And Henrik was responsible for the algorithm development and Jesse for the implementation, and they've been a fantastic team. And what I'm showing you in the plots here is the wall time as a function of the number of carbon atoms for linear alkane chains and then diamond chunks. And the curve that's vanishing off the top there is the amount of time it takes to run Q-Chem's state-of-the-art 4-centered 2-electron integral code to make the J and K matrices. And then the yellow curve is our best resolution of the identity or density fitting method. And you can see the enormous speed ups in CCPVTZ for alkanes and diamond chunks by using resolution of the identity. Then you see something else, which is as the molecule size gets big, resolution of the identity methods scale as the 4th power of system size. The semi-numerical approach to exact exchange scales only quadratically. in the limit. And so once you get above about 50 carbon atoms in a pretty good sized basis, semi-numerical exact exchange is what you want to run, and it enables big molecule DFT calculations in the big basis sets that are necessary for high accuracy. So you save time and energy and you get better chemistry. So we're really excited about semi-numerical exact exchange. As of today, it's limited to only energies, but later on, we will, of course, get gradients in there too. And if you're a Q-Chem wizard and you want to use semi-numerical exchange, set SNK equal to true. All right, so that is that. Well, Coach is a hybrid, and density functionals are organized into rungs of Jacob's ladder, where hybrids are rung 4, and sitting above rung 4 is rung 5, the double hybrids, which are definitely the most accurate functionals available today. And I'm very, very excited to tell you about work that has taken us nearly, well over 4 years to actually do and implement, and is now part of Q-Chem 7, which is, we believe, the world's fastest double hybrid DFT code without sacrificing accuracy, or to be exact, with user-specified accuracy. So what I'm showing you here is a plot illustrating the error in computed reaction energies for a data set, the MME55 data set. There's an example of one of the reactions in MME55 down the bottom right. And the code that is in Q-Chem 7 produces the timings that are on the x-axis that correspond to this blue curve. A very popular implementation of DLP&O in a code that corresponds to a giant sea creature gives the timings that are shown in red. And our first generation that was never released, but was the lead up to this, is shown in green. And so if you pick a target error, let's say you want an error of something like a half a kilojoule per mole, well, then you'll be looking here to get essentially a cut across going this way. And if you compare the sea creature code against Q-Chem, for that same error, you can see that Q-Chem is 3 or 4 times faster. You can also see that Q-Chem can get to precisions that you can't get to with DLP&O just by setting a single user-defined threshold. No different to setting the SCF convergence criterion, really. So we would like to say that Q-Chem 7 offers for double hybrid DFT the shortest compute times for a given precision, the ability to get higher precision than DLP&O MP2. It's the easiest to use. There's only one variable to set, and it also scales nicely in the shared memory environment. In fact, we have a development version that is in distributed memory too, but that's not quite ready to release yet. So this enables a double hybrid DFT on big molecules and really synergizes with semi-numerical exact exchange. And for the wizards who've already got Q-Chem 7, set correlation equal to LMP2 to switch this on, and then do it with standard double hybrid resolution of the identity. In a little more detail, let me just show you what this means. In other words, how much do you have to pay compute-wise and memory-wise to get these results? So if I take a big basis set, def2 QZV PPD, what I'm showing you in these plots on the left-hand side of this slide are the wall time necessary to solve to 10 to the minus 7 precision, 10 to the minus 6.5, 10 to the minus 6, 10 to the minus 5.5, and so forth. For thiophene chains as a function of the number n in the chain length. So in other words, this is then a system that has hundreds of atoms altogether, but 80 carbon atoms in the basic chain. And then here's the peak memory. And you can see that the peak memory goes linear as a function of system size long before the compute time goes linear. So there are 2 advantages of this kind of algorithm. First, less system resources, less memory, so you can run jobs you can't run conventionally. And then second, when the system size gets big enough, you get linear scaling. And so this is shown here. The onset of linear scaling is earliest for the sleaziest cutoffs, and latest for the tightest cutoffs, and the black curves the conventional algorithm. But yeah, so this work that represents the thesis work of Zhenling Wang and the research of the last 2 years of Yao Shen, with a lot of collaborators who are listed as co-authors of the paper, is really a groundbreaker. And here's just an example of a big system computing binding energies for this very large dimeric system. You can just make out a dimer there, and just showing you that we can run these things through with 12,000 basis functions, 30,000 auxiliary orbitals, 750 or so occupied orbitals, and do this in just a few hours on a single node. And so this is very, very exciting. At the other end of the spectrum, we're also excited about the fact that we can do SCFs incredibly cheaply with a new implementation of the GFN XTB model. And this is work that represents the thesis work of Rebecca Toman in my group, Siavesh Maradi and Christopher Stein's group at TUM, and crucial last-minute help from Lucas Takam. And well, if I don't have time to tell you about XTB, but this is more or less a minimal basis valence electron only approximation to DFT that is so cheap that by the time you're doing 300 to 500 carbon atoms, the plot on the right shows you that just diagonalizing the Fock matrix completely dominates. And so the other components that are shown in the pale colors below scale mostly linearly. There's one quadratic one too, but energies and forces are available, and this is very, very freshly implemented and is helpful for finding initial guess geometries, for getting initial force constants, for higher level geometry optimizations, for doing preliminary screens of low energy conformers. But of course, this is not DFT accuracy. This is significantly lower accuracy. So anyway, so GFN XTB is important. Then moving on to slightly more exotic features, if you are interested in the binding of an extra electron to molecules that don't bind an extra electron, those are metastable states, electronically metastable states. And Q-Chem has a long history of development thanks to Anna Krylov's group, Thomas Yago's group, a bit of work from my group, on doing metastable states. And this has now been extended to DFT through work in Thomas Yago's group. And the results are quite encouraging. They're much, much cheaper than than coupled cluster theory, and yet the accuracy appears to be competitive. All right, so that's a charge through density functional theory. I now want to say a few words about correlated methods. This will be brief. Q-Chem's got a very rich, deep suite of electron correlation methods, and that's primarily thanks to, again, the research of Anna Krylov. But we also have some new excitation methods that are worth highlighting. And the mixed reference spin flip TDDFT is newly implemented in Q-Chem for both excitation energies, also transition moments and oscillator strengths, spin orbit couplings, and analysis as well. And this is an improvement over standard spin flip TDDFT for systems where there is biradicaloid character in the ground state and possibly a conical intersection between the ground state and a lowest excited state. So the mixed reference, as is shown in the picture here, includes 2 spin ups and 2 spin downs and spin flips from both. And that gives substantially improved spin purity. So this is an exciting capability at basically TDDFT cost. There are a bunch of others that I will just really mention. There are significant speedups in RICC2. This is done by new graduate student in my group, Rishikesh Ram. There's a bunch of improvements and additions to CC2 for electron attachment, ionization, and excitation processes. This is primarily done in Thomas Yago's group and contributions elsewhere as well. From Wenji Dao's group in collaboration with Junho Lee are a bunch of fast methods, stochastic RI with tensor hypercontraction. And then for the right answer, for the right reason, coupled cluster theory, there are performance improvements that are useful. So altogether, quite a lot new here. And now let me jump to spectroscopy tools. The first one is a feature that represents nearly more than 4 years of work by a very bright student in my group, Xiao Lu. Xiao has worked under my direction to build what we call an in silico NMR lab, where molecules are bathed in fields, and that's how chemical shifts are measured, by then doing the finite field calculation with analytical treatment of the perturbation corresponding to nuclear spins. Q-Chem has long had chemical shift capabilities, but those were based on old 4C2E algorithms. And so if you ask, are those competitive with other codes? The answer is not really, but the new implementation is super nice, and as well as quite novel in its format. So you're really doing quantum chemistry inside a magnetic field here. It's dual level parallel, that is OpenMP for a given calculation, for a given field strength, and then MPI, that is distributed memory parallel, for the different field strengths necessary to do the finite differences. So this automatically scales very well to quite a large number of cores, and the improvement is simply vastly better than Q-Chem's old code. So if I, for instance, begin at the caffeine molecule, and we should all be appropriately caffeinated when discussing Q-Chem 7, and we think about trying to do a nice large basis like PCSeg3, the old serial algorithm is very slow and for a hybrid functional. The new algorithm runs serially, that is doing multiple calculations, 3 calculations in finite B fields. It's 40 times faster than our old code. And then when you use 10 threads, the 40 times speed up leaps to 150 times. So this has completely transformed Q-Chem's NMR capabilities. And furthermore, our old NMR code had limitations on the number of functionals we supported, and now those limitations are gone. We support modern range-separated hybrid meta-GGAs, as well as all traditional global hybrids, and so this is something that we are very proud of, and this is taking maybe 120 seconds to explain 4 years of work. I can't emphasize enough how crucial Xiao's effort was to making this happen. And this dovetailed with Q-Chem, where Kaushik had been working on MPI. And so the collaboration then was Xiao doing this development work and then interacting with Kaushik to make it MPI capable, to give these truly enormous speedups for the high quality basis sets you want to use. And then if you say, well, I don't really just want to do this enormous PCSeg3. What about PCSeg2? Well, then it's only a 400 times speed up. Is that right? Yeah, basically, it's essentially speed up drops here somewhat, but still very nice. Then let me just mention electronic circular dichroism, thanks to work in Wanzhen Liang's group in Xiamen University. We now have ECD with TDDFT that then extends to larger molecules, the existing ECD with coupled cluster capabilities that Q-Chem has. And this is important for absolute structure determination of enantiomers. And so this is a nice capability if you need it. And another very, very good thing to have. All right, so far I've been talking about the numerical experiments, but Q-Chem is also full of ways to analyze the numerical experiments, which are quantum chemistry calculations. And so in addition to our historical leadership in analysis, which includes energy decomposition analysis, symmetry adapted perturbation theory from John Herbert's group at Ohio State, and many other things, we have a bunch of new features. And this one's from my group. This is to do with what is the most compact, what is the optimal way to describe the density rearrangement from an initial determinant to a final determinant. And and if you've heard of the natural orbitals for chemical valence, or NOCVs, that are, for instance, used in the ADF code for energy decomposition analysis, well, these OVOCVs are a simple but crucial improvement on the NOCVs. So the NOCVs do not properly reveal the number of electrons promoted when you do something like allow charge transfer versus forbid it. It's well known that the NOCVs substantially overestimate charge transfer. But the OVOCVs give you the correct Hilbert space picture of the number of electrons promoted, and it actually matches my friend and collaborator and Q-Chem founder, Peter Gill, his definition of the excitation number that they published in 2018. When you use OVOCVs in energy decomposition analysis, they give the identical energy contributions to the NOCVs, and at the same time, they provide good values for the number of electrons promoted. So really, this is a replacement for NOCVs. And most beautiful is the picture. So this is the halogen bond between this carbon-sulfur double bonded compound and the iodine molecule. And this is the occupied this is the occupied orbital for chemical valence, and this is the virtual one. The virtual one is on iodine, and you can see it looks sigma star-like. And the occupied one is on the sulfur, and you can see it looks like a lone pair. And so this is showing you the lone pair into sigma star donation. From John Herbert's group are valuable new metrics for charge displacement that are rigorously invariant with respect to orbital rotations, unlike metrics used in some other software packages. And those are useful for diagnosing charge transfer character in TDDFT calculations. And there's a nice illustration of the principal NTOs and the metrics for hexacene excited states. And this is work done by John's student Mandel with John. From my group is the Earth mover's distance, which is part of the thesis work of Zhe Wang. And I would like to argue that the Earth mover's distance is the perfect scalar to measure the extent of charge transfer. The idea about Earth mover's distance is you begin with a figurative pile of dirt called the supply pile, which is the density in the ground state that is about to be changed or rearranged from a supply pile into a demand pile. And the question is, what is the least amount of shoveling you can do in order to rearrange the piece of the ground state electron density into the excited state? So that is the Earth mover's distance, and Q-Chem, as far as I know, is the only major electronic structure code to include this metric, which, by the way, can be applied not just to TDDFT, but to any excitation process where you have a wave function and thus a density for the ground state and the excited state. And it can even be applied to any rearrangement of density. You just need the initial state and the final state. John Herbert's group has a long history of extensions of symmetry-adapted perturbation theory that give you the accuracy advantages of SAPT and directly attack the cost disadvantages of SAPT. And so Q-Chem 7 includes new many-body dispersion models that come both from John's group and also from Ka-Un Lau's group at VCU. So we're very grateful for those contributions. And let's see, and another thing to mention is external interfacing. So Q-Chem is not an island, but talks to graphical user interfaces, talks to Python. It has a bunch of capabilities that I don't have time to tell you about regarding archiving and the ability to do handshaking with Python. We also have an embedding interface for CP2K to talk to a dynamics code. And this is work done by John's group in collaboration with Christopher Mundy's group and others, including Christopher Stein. And so this is very nice in order to couple a wave function active region with periodic DFT. It does this by exact projection. There are tutorials on our website to learn how to do QMMM. Q-Chem has extensive QMMM capabilities involving a Q-Chem Amber interface. There's also a Q-Chem Charm interface. And then, as I will tell you about in the final minutes of the webinar, we also have our own advanced molecular mechanics under development right now. And you can scan the QR code to learn about the Q-Chem Amber interface. All right, so that's sort of it for that's roughly 35 minutes on core Q-Chem itself. My last topics are to now tell you about two external packages, brand new packages that extend Q-Chem in two different and very important complementary directions to core Q-Chem itself. The first is periodic solids, and the product is called QC-PBC, the PBC for periodic boundary conditions, and this is a long development, really probably at least 6 or 7 years altogether, since it began as a skunkworks project in my group that Junho Lee led while he was still a graduate student. And now he's a very successful leading faculty member at Harvard, and QC-PBC has been taken to fruition thanks to the leadership of Junho and thanks to lead developer Adam Rettig, who was jointly employed between Harvard as a postdoc and Q-Chem as a consultant to make this happen. And so QC-PBC is a general purpose solid state modeling code that includes standard density functional theory capabilities with special capabilities for hybrids. So the performance for hybrids is really worth highlighting. And then it isn't just limited to SCF, it also includes MP2, Laplace transformed variant, and MP3, and even couple cluster at the gamma point level. It has a very powerful Python interfacing, PyQC-PBC. Geometry optimizations are allowed, implicit solvation is catered to, analytic frequency and phonons are possible. And again, this is worth highlighting because very few codes have analytic frequency and phonon calculations, especially for hybrid functionals. And the QC-PBC development effort has concentrated heavily on parallel performance, and you can see how nicely the wall time for the silicon carbide benchmark comes down as the number of cores is increased. So it has very, very good parallel performance. So this is an exciting, completely new capability for Q-Chem, and it comes bundled with Q-Chem 7, so external package. Well, what you can do with it is limited to your imagination, but a great deal of work is going on applications primarily at Harvard, where the code has been developed, and so there have been applications to explore the BWS2 method that was developed in my group recently for molecules to extend it to solids. The energy decomposition analysis methods that have made Q-Chem a leader in understanding molecular interactions have been extended to allow the exploration of molecule surface interactions in QC-PBC, or layered interactions, all kinds of possibilities here. So this is again a powerful extension of existing methods. Work on applied voltage to do things like simulate corrosion. These are very elegant bias-dependent plots of free energy as a function of pulling an atom away from a surface to model silver corrosion. This can be done in QC-PBC. And it points out the fact that there is a very nice Poisson-Boltzmann model for not just solvent, not just continuum solvent, but continuum electrolyte that makes this possible. So that's a very nice feature in QC-PBC. Another nice feature, this has come from my group's contribution to this small contribution to this development effort, is improving the approach to the thermodynamic or bulk limit to to model a system with a periodic unit cell and to actually get the true bulk limit, you have to converge the number of K points. So in other words, the extreme minimum of the number of K points is a gamma point calculation. This is these are I'm showing one polymorph of oxidyl dihydrazide and very large number of K points in the X, Y, and Z directions still gives slow convergence towards the bulk limit for the energy per unit cell. And this is, of course, offset here. By comparison, if you use a new method cooperatively developed by Lin Lins and myself with our joint students, Juan and Stephen, you see much, much faster convergence. And as shown in the right plot, the additional compute time to do singularity subtraction, thanks to Juan's highly efficient implementation in QCPBC, is very, very tiny. So this is a powerful tool that is not routinely used in solid state modeling at the moment, and it's particularly important for hybrid functionals, and hybrid functionals are the particular strength of QCPBC. So this enables greater accuracy. So anyway, that's just a little taste of QCPBC, and this is a project that we hope will strengthen and evolve with time. And then we have one more external package that I want to mention, which is MChem. And MChem is short for molecular mechanics and chemistry. And this work was spearheaded by Teresa Head-Gordon's research group at Berkeley, and in particular by Jagna Wittek, who was first a postdoc in Teresa's group and then became a Q-Chem employee and consultant. And Jagna is responsible for the development of the infrastructure with a lot of contributions from many other members of Teresa's group in particular. So what is in MChem and why is it special? And by the way, MChem is not quite released, but is coming very soon. So MChem has a focus on not just the conventional fixed charge or amber or charm type force fields, but advanced force fields, polarizable ones, so amoeba and the advanced generalizations of amoeba that are developed in Teresa's group, and also reactive force fields like ReactFF that can make and break chemical bonds. MChem includes all of the kind of simulation capabilities necessary for the condensed phase. So in contrast to the hard condensed matter that was the focus of QCPBC, this is now soft condensed matter at finite temperatures. So we need thermostats and barostats. We need ways to propagate the electronic degrees of freedom in a polarizable force field at the same time as you propagate nuclear dynamics. You need builders for the front end, and you need ways to then pass the resulting trajectories to other codes for analysis. So MChem will support all of this. And so you should be aware of advanced force fields because of their higher accuracy. Be aware of ReactFF for the ability to make and break bonds if you can't afford to do full quantum mechanics. And then there's ways to develop parameters for cases where you don't already have them. There's Python interfacing, and then Jagna Wittek has put a great effort into MPI and OpenMP individually and their hybrid applications. So basically that is a little peek at MChem. And this more or less brings me to the end of my webinar. So go visit our website to learn more. You can browse the Q-Chem 7 manual, see all the documentation. You can visit the talk forum to hear what other users are discussing. Q-Chem runs periodic workshops, periodic webinars. Oh yeah, like this one. And there are lots more Q-Chem 7 features that are highlighted on the website, so you can scan the QR code and look into those if you would like. And so yeah, it's really been quite a pleasure to tell you about this and to try and convey my excitement at the collective effort that it has taken our several hundred developers to put together all the advances that have occurred in our core density functional capabilities, our parallel computing capabilities, our handshaking to external codes, our new post-SCF features, our new analysis features, and the new external modules QCPBC and MChem. I think it's no exaggeration to say that Q-Chem 7 is the most major of Q-Chem's major releases ever. I'm super happy to be able to tell you about it. And it remains for me to acknowledge the Q-Chem team. So Andrew Gilbert is our operations leader and has been doing a wonderful job coordinating between the Q-Chem team and the academic team and the Q-Chem board. Kaushik Nanda introduced me, and you heard about his robust SCF contributions. Quan Yu is responsible for a myriad of behind-the-scenes details as well as some in front-of-the-scenes details. Sarah is in charge of the office and marketing. Shannon does a great deal of things to do with website marketing, release features, and Shintian is responsible for most of the performance optimization. Q-Chem's board tries to steer this project, and I'm grateful to all of them for their engagement and their effort. And we couldn't do it without the developer community. And so again, there's an open door if any of you are listening and thinking, I'd like to try and help build Q-Chem 8. Well, we need new builders for Q-Chem 8, so please consider joining. And thanks everyone for listening. Again, if people don't buy the code, if people don't use it, we can't support the team, we can't sustain the effort. So I encourage everyone who's listening and thinking about trying to explore this to jump in and get a license for Q-Chem 7. And thank you for listening. I'll stop there.
All right. So thank you, Professor Hidgorden, for the nice talk. So there are about 10 questions, and we have maybe 10 or 15 minutes left in the webinar. So I'll read some of the questions. So the first question is about the core double ionization potential. So this is related to slide 8. So can we calculate this double ionization potential for core excitation, so core electrons? So how is the convergence behavior?
Well, I have no personal knowledge of that, but let me try and ramble back to slide 8, and I'm not sure if either you or Quan Yu would like to weigh in on that. This is, you mean this slide? Yep, let's just say I'm not sure I can comment, but Q-Chem, but our range of options to converge both SCF and couple cluster calculations is second to none.
So you may try to look for CVS DIP methods in the manual. I'm not sure if couple cluster methods are available for CVS DIP, but they might be. You need to check the manual for that. So we move on to second question. So this is about dispersion correction with coach functional. So both VV and D4 from the output. So I'm not.
Okay. I can comment on dispersion corrections in Coach because I spent a lot of time worrying about them. So if you ask what if anything is wrong with omega B97 M-V for dispersion in large molecules, the answer is nothing that we could really detect in systems up to the size that we benchmarked on when the functional was developed. However, liquid water will be too dense when you simulate it with omega B97 M-V. Why? Probably because it is lacking three-body dispersion. So we then see hints of this when we look at things like the S12L data set. And so in the benchmarking and development of COACH, we finished up including the VV10 pairwise additive dispersion and then D4 three-body dispersion. So in other words, the D4 bit is just the three-body part in order to capture the repulsive part of dispersion and avoid the overcorrection that actually occurs in many-body dispersion in very large systems. So please consult the COACH paper for more details. But I think that's what you're interested in.
Right, thank you. So the next question is about what about X2C, all electron relativistics in the NMR code, and X2C for energies.
Okay. Well, thank you for asking, because the wonderful Xiao Lu, student in my group who's responsible for the in silico NMR lab, has also implemented the analytical one electron matrix elements necessary for X2C and is on his way to including the spin orbit coupling. So that means that the way Q-Chem did X2C in version 6 was actually finite differencing, and this is no longer necessary in Q-Chem 7. Automatic machinery to decontract and then recontract the basis to make X2C optimally efficient is not yet available in 7.0.0, so you need to do it at the input file level. But Kaushik, Xiao, and I will be discussing how to automate this in the future. So that then brings up an opportunity, which your question alludes to, which is how helpful would X2C be for NMR? And the short answer is, well, NMR is a property at the nucleus, so it is sensitive to relativistic effects as you move to heavier elements. So at the level of hydrogens and carbons, the effect is likely to be negligible and you wouldn't see any useful improvement. But if you're interested in NMR of heavy elements, then there will be future Q-Chem capabilities, we hope, that will explore the synergy between our in silico NMR lab infrastructure and our ability to now do SCF with X2C, even including spin orbit effects.
Thank you. So the next question is OVOCVs for open shell is equal to 1/2 monomers and coupling to low spin dimers. So will that work for phenylenedimer dimer?
That's a very good question. I think we have an open shell implementation, but I'm not absolutely sure without checking. And the phenylenyl dimer is the famous pancake bond, where you take 3 benzene rings and you fuse them together to make C13H9 dot. And then you put 2 of those together and you get the dimer, which is actually diamagnetic. But if you ionize it or electron attached to it, you get 2 other stable species that would be S equals 1/2. And OVOCVs are most natural when the number of electrons is conserved, but can be in principle generalized to the case where you ionize or electron attach. This is not something that I think the code currently supports. So you have to keep the number of electrons constant between the initial and final determinants at the moment. We have some code, thanks to the work of both my student Hengyuan Shen and a visitor Haobo Li, to extend OVOCVs to orbital optimized density functional theory. So some kinds of excitations can now be analyzed in this way, and you can separate the the contribution of say an excitation from the relaxation of the spectator electrons, which is a nice application. So anyway, so that's at least a partial answer to your question.
Great, thank you. So the next question is how does the coach functional work in case of excited states involving significant charge transfer character?
Okay, great question. And we don't have a whole lot of data on that. My view about developing density functionals is that we do not want to use TDDFT as part of the development process because it invokes the uncontrolled adiabatic approximation. Having said that, it is a range-separated hybrid, so it should have performance similar to other good range-separated hybrids for TDDFT for charge transfer. And having said that, let me say that I think if you have a pure charge transfer state, the best way to do it is with orbital optimized DFT and just treat the excited state as either a ROX or a single determinant, and then you will get great results as long as the excitation is pure charge transfer.
Right, thank you. So the next question is what ensembles are available in MChem?
Ooh, I believe standard, canonical, microcanonical. I'm not sure about grand canonical. So initially I think you can count on microcanonical and canonical. And there's probably one or two others, but I'm only a pedestrian statistical mechanic, so I'll have to we can get back to you on that.
Right. So if there are any questions which are left unanswered, please feel free to contact support@qchem.com and we can relay your questions to the developers. So thank you. Now, the next question is about X2XC, for example. So what about it?
X to C again.
X2XC, for example. X2XC, maybe it's not, maybe there's a typo.
Yeah, so well, to the relativistic X to C or exact two component, if you're listening and are not quite sure what we're talking about. So X to C is exact two component relativity and is an area of active development in Q-Chem and very helpful for computing core excitations. And I'm not sure what X to C actually is, so I guess I have to stop there.
Yeah, it's X2X and then C. X2XC. I think it's a typo.
Okay.
Yeah. So we move on to the next question. So there's the student in France, and his question is, since conventional TDDFT can struggle with strongly correlated systems, how does MRSF-TDDFT in Q-Chem 7 improve that description, and what limitations still remain compared with multi-reference methods?
Ooh, okay. Great question, and I'm not the perfect person to answer it because this is not my project. But this implementation of, let me say what I think I know, and so what I think I know is that the simplest kind of strong correlation is when two electrons are strongly correlated, and that would be, for instance, a single stretched bond or a biradicaloid like the phenylenyl dimer that got brought up briefly before. And so the characteristic of those systems is that they have a low-lying triplet, because if two electrons are strongly correlated, they're not strongly paired. So I'm not sure if you can see my fingers or not, but the unpairing energy to go from this configuration to that configuration is kind of low. And so that's the scenario in which mixed reference spin flip TDDFT should be good. In other words, it can in principle handle the entanglement of two electrons. But suppose four electrons are strongly entangled. In other words, suppose you wanted a 4-in-4 active space. Well, then this mixed reference spin flip TDDFT would be inadequate. So the main question in strongly correlated systems is how many pairs of electrons are strongly correlated. If that answer is primarily one pair, then that's the regime in which single spin flip methods work reasonably well. And having said that, I haven't actually got any personal experience with how well it works. We expect, I think, that it will depend pretty strongly on the fraction of exact exchange in the functional, and so there may be still some heuristic tuning. But I think the hope is that the dependence on the fraction of exact exchange will be lower than in standard spin flip TDDFT. So yeah, so maybe that's a partial answer.
All right, thank you. So there are two more questions. They are related to the basis sets in QCPBC, so I will combine them. So the first part is, can you tell me which type of basis is used for solid material in this code, in the QCPBC code, I suspect. So is it possible to simulate the correlated solid materials using this code? And yeah, we are using GTO-based basis, so I can answer that.
Yeah, there is flexibility here. It depends on how the resolution of the identity is done. So there is a resolution of the identity that uses plane waves. That is very badly suited to simulating core electrons. And there's a resolution of the identity that uses the same auxiliary basis sets that we use in conventional quantum chemistry, and that is well suited to simulating core electrons. So it depends which options you set as to which basis sets you can use, is my understanding.
Thank you. And the second part of this basis set related question, so the website describes it as GTO based, but I recall it being implemented similarly to CP2K, which also uses plane waves as an auxiliary basis. So is QCPBC's approach actually GPW-like, as in Gaussians plus plane waves, or is it some purely GTO-based?
As I said, my understanding is that there are two algorithmic options. The first one is CP2K-like, where the atomic orbital basis is Gaussian and the resolution of the identity is plane waves. And the second one is where the Gaussians are used as the resolution of the identity as well.
Yeah, thank you. And so there's a comment, I think it's related to the OVOCVs question earlier. So it's so too sad that OVOCVs for pancake bonds, that is what the user is interested in, and unfortunately it is not available in the X SAPT code as well.
Oh, well, the XSAPT code doesn't have a clear single determinant wave function. So I maybe didn't say clearly, but OVOCVs solve the problem of what is the most compact representation of the change in electron density from one determinant to another determinant, one single determinant to another single determinant. So it's perfectly suited to cone-sham DFT, where the single determinant is the reference for the electron density. But XSAPT and SAPT methods are not single determinant methods. They have multiple configurations. So an interesting challenge for future people interested in doing analysis projects is how should that be generalized to wave functions that are more complicated than just a pure one determinant. So, but having said that, I think you can probably pick a suitable one determinant approach and perhaps get some insight into electron density rearrangements in the pancake bonds, but not XSAPT.
Okay. Thank you. So that was the last question. So with that, we'll conclude our webinar. So at this point, I'd like to thank all the larger Q-Chem developer community for their invaluable contributions, and to the Q-Chem software and their continued collaboration. And I'll thank Professor Hedgorden for the wonderful seminar on the new features in Q-Chem 7, and all the attendees for their questions and their time. So thank you, everyone, and have a happy Tuesday.